Hi, I'm Brad Davis, one of the authors of Oculus Rift in Action. One of the things I've seen asked and been asked is how to use OpenCV to display webcam captured video in the Rift. This technique has obvious applications for telepresence and augmented reality, so today I'm going to walk through an example application which takes images from a Rift-mounted webcam via OpenCV and renders it to the Rift using OpenGL on the Oculus SDK. The full example is on GitHub and will be covered more extensively in Chapter 14 of our book. In this video, we're going to look at these elements of the example, starting with asynchronous image capture. Image capture does need to be asynchronous because pulling data from a webcam or other potentially high latency source should always be done on a separate thread from rendering. Waiting on an image from a camera, especially one that is probably running at a lower refresh rate than the Rift, isn't something you want to be doing on your rendering thread, which should always be running at the Rift's native refresh rate. In addition, when you capture an image, you typically want to capture the pose associated with the camera. If you've got a camera mounted on the headset, this means querying the Oculus SDK for the pose at the time of image capture. If you're dealing with telepresence, like cameras mounted on a robot, then capturing this data is slightly more complex. For this video, I'm just going to look at the first application, a Rift-mounted camera. Because the image data is captured on one thread and displayed in another, we need to make sure that we serialize access to anything that will be used on both threads. For this, I'm using a small class that lets me implement a producer-consumer model. The producer derives from this class and implements the loop function. Once a capture has occurred, it's stored using the setResult method. The consumer owns an instance of this class and can simultaneously check for and fetch new data by calling getResult. If a new capture is available, it's returned in the passed output parameter, and the method returns true. Otherwise, it returns false, indicating there's no new data. In our case, the data we want to capture is a combination of the webcam image and the head pose at the time of capture, so we create a small structure to encapsulate that. Here's our actual capture class, which is derived from the capture handler. It contains an OpenCV video capture instance to interact with the webcam and an OVR HMD instance, which is required to fetch the head pose. In our constructor, we open the camera and set it up. The capture loop is the important part. It should be running for the duration of our application in order to capture images and make them available to our consumer, which we'll cover in a moment. In this example, I'm capturing the head pose immediately before I call the image retrieval functions. The function getTrackingState accepts as a parameter the time for which the pose is desired. If you simply pass in getTime in seconds, it should return you almost exactly the current head pose. As you add time to that value, it attempts to predict what the pose will be at a future time. Here, I'm actually subtracting a value from the number. This is because I've found that by the time that I call videoCapture.grab, the image I'll eventually get is about 40 milliseconds old. Mind you, this isn't rigorously tested. It's just a number that I kind of zeroed in on through experimentation. I should also note that the Oculus SDK won't normally allow you to predict into the past this way. If the time passed into getTrackingState is before the current time, it just sets the delta to 0 and gives you the current pose. I've tweaked my copy of the SDK to disable this specifically so I can use the pose prediction mechanism with a high latency input source like a webcam. Note that when we capture the image, we also flip it vertically. OpenCV and OpenGL use different directions for the y-axis of an image, so we have to do this at some point in the pipeline, or our image will appear upside down on the screen. That takes care of the producer half of our model. Now let's take a look at the code that consumes these images and renders to the Rift. For doing this, I've created a Webcam App class, which is derived from RiftApp. RiftApp is a class I've developed for all of the later examples in my book. It takes care of the bulk of the interaction with the Rift and OpenGL, requiring only that I implement a renderScene method, which will be called twice per frame, once for each eye. I can also optionally implement an update method, which will be called once per frame, and an initGL method, which is called once at application startup after the OpenGL window and context have been created. Of course, to render anything in OpenGL, you need a shader, some geometry, and in our case, a texture containing the image captured from the webcam. We'll set these up in the initGL method, and then use them in the renderScene method. Here, I'm using my own wrapper classes for the GL objects. If you're familiar with OpenGL, the usage should be pretty self-evident, and if you're not, the source code is available on GitHub so you can see the exact OpenGL calls made. Of course, if you're using your own rendering framework, you probably have your own set of classes. The initGL method initializes our OpenGL members. Most of the complexity is hidden behind the class wrappers, so this is just giving a basic idea. However, the setup of the geometry requires some extra explanation. I'm using a utility function which creates geometry for a rectangle with a given aspect ratio and a size for the longer dimension. But how do I determine the size? I want to render the image in such a way that it takes up the same field of view that is actually captured by the camera, or as close to it as possible. I happen to know that my camera has a horizontal field of view of about 70 degrees. I also control the distance from the camera at which I will render the image. This turns the sizing into a simple trigonometry problem. If d is the distance at which we will render and theta is half the overall horizontal field of view, then x over d is equal to the tangent of theta. Therefore x is d times tan theta. That's what we assign to the scale value, but that's only half the width that we want to render, so we double it when we pass it into our getQuadGeometry function. Our update function is responsible for moving the image from an OpenCV format to something that OpenGL can use. We check if there's new data available from the capture handler, and if so, we consume it by loading it into our OpenGL texture. This works because OpenCV typically stores its image data from webcams in the same format we'll need to pass to OpenGL. Of course, captured images usually have the blue and red channels reversed from OpenGL conventions, so we specify GL-BGR instead of GL-RGB. This lets OpenGL handle the details of flipping the channels. If your camera isn't providing images in a 3-channel 8-bit color, you should make sure to convert them to that format in your capture thread. Finally, we get to our renderScene function. By the time this function has been called, our parent class has already captured the Rift head pose and applied it to the top of the model view stack, so we can just render as if our camera is already set up, because it is. Now, for any VR application, I always draw a skybox of some form. Having a background that fills as much of the field of view as possible, and which is perfectly responsive to head movements, or at least as perfectly as is achievable with the Rift, provides a good baseline in terms of VR presence and comfort. Webcams typically don't have the kind of performance that you'd need to provide a good VR experience with the captured image alone, so having this background improves presence and reduces the chance for motion sickness. Now I'm ready to actually render the captured image. However, as I said, the model view stack is already set up with the user's head pose. In our case, that doesn't help us. We actually want the image to be rendered relative to the headset, because that's where the webcam is fixed, not relative to the world. So we need to reset the model view to an identity transform. But we also don't want the image to be precisely fixed in the user's view. Instead, we want to account for the differences between the current head pose and the pose at which the image was captured. We do this by finding the delta transform between the capture pose and the current render pose, and then applying that delta to the model view stack, thus rotating where our image will be rendered relative to our point of view. We translate the image away from the point of view by the same value we used in the trigonometry, so that it will take up the correct field of view. Then we bind the texture and render the geometry. Lastly, I render some diagnostic information to the screen showing both the rendering frame rate and the capture frame rate. Let's take a look at this in practice. This is a view of my backyard. As you can see, as I move my head, the captured image window has a tendency to lag behind. This is because of the compensation for the difference between the capture pose and the render pose. However, despite this lag, or rather because it's intentional lag that has been calibrated for my camera latency, the images from the camera remain relatively stable compared to the skybox background. Of course, no discussion of the Rift is complete without some reference to the screen door effect. One topic that I've skipped over is that of camera distortion. Like the lenses in the Rift, the lenses on a camera, including webcams, introduce some distortion into the image. Ideally, you'd want the image you render in OpenGL to have no such distortion. OpenCV includes mechanism for calibrating cameras against test patterns to find the camera lens parameters and even correcting the distortion. However, while it's possible to do this correction on the capture thread, I don't recommend doing so, as it will likely drastically reduce your capture frame rate. Ideally, if you wanted to correct the distortion, instead of rendering the captured image to a simple rectangle, as I've done, you'd use the camera parameters to create a distortion correcting mesh in OpenGL and render to that mesh instead. With any reasonable GPU, this will have much better performance than correcting the distortion on the CPU. Today we've seen how to easily get OpenCV captured content into a Rift-based application by pushing the capture code into a separate thread, understanding how to make OpenCV images available as OpenGL textures, sizing and positioning the image within the scene correctly given the camera field of view, and providing a comfortable VR experience by accounting for the differences between image capture poses and render poses. Thank you for watching. Check out my GitHub repository for additional examples, and check out my book for more details on developing for the Rift.